Okay, now we're going to look at distributions, or the x-bar distribution, but the original distribution is not normally distributed. Now this is where our central limit theorem comes into play, okay? If our original x distribution is normally distributed, then our x-bar distribution will be normally distributed and we can change it to z, no big deal. But if the x distribution is not normally distributed, then the only time that we can change x bar into a z, okay, the only time our x bar distribution will be normal is if our sample size is at least 30. So when we read our problems, if it does not say that we have a normal distribution, we have to check the sample size. If our sample size is not big enough, then we cannot work the problem. Okay? So let's look. Fire department response time is the length of time it takes a fire truck to arrive at the scene of a fire, starting from the time the call was given to the truck. Response time for the Castlewood Fire Department follows a mound-shaped and symmetric distribution. The response time has a mean mu equal to 8.8 minutes with standard deviation sigma equals 2.1 minutes. If a random sample of 32 response times is taken and the mean response time x bar is computed, find each of the following. Well, this is asking us to find the probability of an x bar. However, if you notice, nowhere in the problem did it say normally distributed. It just said we had a mound-shaped and symmetric distribution. But if we look at our sample size, we can see right here n is 32. So it really doesn't matter. Since our sample size is larger than 30, we can go ahead and work these problems out just like we did before. Okay? So just the same way, this is going to become the probability that z is less than or equal to x minus mu, or x bar minus mu, excuse me, 8 minus 8.8 over, and then we have sigma divided by the square root of n. So 2.1 divided by the square root of 32. So this is going to be the probability that z is less than or equal to. We work this out. Again, we always go 2 decimal places. We get negative 2.15. This is an area to the left, so I'm going to go to my z table. The negative side, negative 2.15, and we get 0.0158. So 0.0158. Okay? Now, if this had not had a large enough sample size, if this had just had a sample of size 20, we could not work this problem out. Okay? All right. The probability that z is greater than or equal to. All right, we're looking at a probability of an x bar, so we're going to use our x bar, 9 minus mu, 8.8, over sigma divided by the square root of n. So 2.1 divided by the square root of 32. So this is the probability that z is greater than or equal to 0.54. Now this is an area to the right, so when we look up 0.54, we're going to get an area to the left, so we have to do 1 minus that. So 0.54, 0.7054. When we subtract that, we get 0.2946. All right, one more time. All right, this is going to be the probability. Now, we have to do this for both of these. So our x bar, 8.5 minus 8.8 divided by, and then 2.1 divided by the square root of 32 is less than or equal to z is less than or equal to, and then we do this with the 10. So 10 minus 8.8 over 2.1 divided by the square root of 32. So this equals probability, let's see, negative 0.81 is less than or equal to z is less than or equal to 3.23. All right, so this is between. When I look up 3.23, that's going to give me my larger area to the left. When I look up my negative 0.81, that'll be my smaller area to the left, and then I have to subtract those to get the area between. So 3.23, 3.23 is 0.9994. When I go to negative 0.81, 0.2090. Subtract those. Oops. We get 0.7904. Okay? So let me know if you have any questions about the X-bar distribution.